Hi folks, Mr. Long here to do a screencast. And our screencast today will be on what's called the fundamental theorem of calculus, okay? And fundamental theorem of calculus allows us to determine area under curves, but it has some really specific and precise meanings and precise notation. And so that's what we're going to try and develop today. Okay, so this symbol here we looked at previously, just briefly, and that we know it means get the area between x equals a and x equals b under the curve. We say under the curve, but it's really between the curve and the x-axis for f at x. Okay, so let's go through some examples here. So here's the first one. So let's start with just the math part to make it simple and the notation. So here's the question. Calculate the area between the x-axis and y equals f at x from x equals 1 to x equals 4. So let's go down to the graph. Well, what is our f at x? It's a nice simple graph. Y equals 5 or f at x equals 5. Okay, and I'm trying to get the area between the x-axis and y equals 5. Okay, so and the question is, why are you using all this notation, Mr. Long, in formality when it's such a simple question? Well, because we'll end up with, as you know, things will get much more complex, and it's a lot easier to understand the notation and the meaning if you start with some simple examples. Okay, and we're going from x equals 1 to x equals 4. Now it is a real life scenario. It's snowfall or snow melt rate graph in centimeters per hour, and the x-axis is hours after a storm started. We're not going to get into that for a minute. Okay, so let's go through this then. So there's our notation right here. So this means starting at x equals 1, that's 1 hour, up to x equals 4, that's 4 hours. I need to get the area between the x-axis and the curve f at x. dx and f at x refer to delta y and delta x. So if we have a rectangle, we know that area is just length times width, which is just our base times height, right? If it's a triangle, it'd be base times height over 2. But for a rectangle, it's base times height, right? So if we think about this, it's just delta x goes side to side, delta y goes up and down. Okay, so in this case, you know that f at x is the y value. That's delta y. dx is short for delta x. Okay, dx is the width of each rectangle that you use. It has a more precise meaning based on the limit a little bit later on, but for now, as long as we think of it as delta x and delta y, we're in good shape. Okay, so in this case, our delta x goes from x equals a, which is this value, to x equals b. Direction is important. From 1 to x equals 4. Well, how far is it do you go from 1 to 4? It's 4 minus 1, which is 3. Okay, and we can look at that on the graph here. I'm going from x equals 1 to x equals 4. And you see the calculation there again. And you'll have a copy of this handout, right? So you'll be able to annotate it as you see fit. Okay, then we go and we look at delta y. Well, what does delta y do? We always go in for delta y. If you notice, it tells us which direction to go on the x-axis from 1 to 4. It doesn't tell us what direction to go on the y-axis. So we have a convention. The convention is the sign of delta y and value of delta y is based on the distance from the x-axis, which is y equals 0, to wherever the function is. Okay, to wherever the function is. So we always start at y equals 0. So in this case, I'm going from y equals 0 all the way up to the function. The function is y equals 5. So delta y is just 5 minus 0, or 5. So then what is the area? Well, so I know that this is 5. So that tells me that the area, which is the integral from 1 to 4, f at x dx just equals delta y, delta x multiplied together because it's a rectangle. Well, in this case, delta y is 5. Delta x is b minus a, which is 4 minus 1, which is 3. So the area is 15. Okay, the area is 15. So that's how you do the mathematics of it. Well, what does that mean in a real life context? Well, here's the real life question. How much did the depth of snow change by from 1 hour to 4 hours after the storm started? Well, I have to look really carefully here because I'm talking about change. I'm not talking about depth of snow because it doesn't say anything. This storm could have been, so if you think about this, right? We know that 15 centimeters of snow fell. So maybe it was the first snowfall of the year, in which case we would have a depth of 15 centimeters. But what if it was the end of January and there was already 100 centimeters of snow on the ground and another 15 centimeters fell? Well, then you'd have 115. So the mathematics of the fundamental theorem, right now at least, don't give us enough information to get the depth of snow. It's only the change in depth, okay? Another thing they call the fundamental theorem is the net change theorem. So now we're going to add this real life context. So the first question you always have to ask, the rate on the y-axis is centimeters per hour, and you're multiplying by hours on the x-axis, delta y, delta x. So we're definitely going to get area as, so those are our delta y units, this is our delta x units, and that's going to be just centimeters. So therefore, we know that, like we just did the math of this, and that works out to 15. That means the depth of snow changed by plus 15 centimeters from 1 to 4 hours. In other words, going from 1 hour to 4 hours, the snow got deeper, okay? The snow got deeper. We don't know how deep it is. We just know it got deeper by 15 centimeters, okay? It got deeper by 15 centimeters. Okay, let's look at another question. What if I just reverse the direction? And now it says, start with the math question notation. Now I'm going to change it from, we're going to go from x equals 4 to x equals 1. Okay, so instead of starting at x equals 1, I'm going to start at x equals 4. So let's look at that in the picture. So in other words, I'm starting at x equals 4, and I'm looking at the change, or the area that occurred from x equals 4 to x equals 1. Well, that should tell us right away I'm moving to the left. Well, what is delta x if I move to the left? Delta x has to be negative, okay, because I'm moving to the left. So go to this, and we can see here, it means that we always start at x equals a, we always end at x equals b. So I'm going right to left. Okay, so here's my new equation. It's still delta x, delta y, except let's look at our delta x. I'm going from x equals 4 to x equals 1. So delta x is then 1 minus 4, which is negative 3. Okay, 1 minus 4. So because I'm going from 4 to 1, I'm going to the left. Okay. You can do 4 minus 1 and just make it negative. It doesn't matter, really, as long as you understand that delta x has to be negative. Now, delta y is still, we always measure delta y starting at the x-axis, y equals 0, and we're going up to the function value, f of x, of 5. And it's a nice, constant, easy one. So that's still going to be 5. So now when we do the area, though, the area in this case is the integral from 4 to 1, f of x dx, which equals, multiplied by dx, which equals, again, delta y, delta x. And that equals, delta y is still 5, but delta x is now negative 3 because I went to the left, right? Again, just left, right, up, down, right? You just get your signs that way. This is just the math. So now the area is negative 15, right? The integral is negative 15. Whereas in our first example, it was positive 15. So what's the only thing that changed? Our delta x is negative because we went from, if you look at this, we went from right to left. We always start at this bottom number on the integral. By the way, they call these the bounds of integration, the boundary. Okay, so it's negative 3, I get that. Let's now add a real life connection to this. So now imagine that you walk outside after 4 hours of it having a storm, a snowstorm, okay? You walk outside after 4 hours. Okay, so, well, actually, sorry, you go outside after 1 hour, then you go outside after 4 hours. So as you look back, is the snow, everything's relative now to 4 hours because we're starting at 4 hours. So if I start at 4 hours and look to 1 hour, was the snow deeper or less deep at 1 hour? Right? So remember, we start at 4 hours and compare to 1 hour. So how much if I look back in time, is there less snow or more snow, right? Because delta x is negative. I'm moving to the left, right? I'm moving to the left. Okay, well, let's go through the units on area are still going to be centimeters. So we got this negative 15, means the depth of snow changed by negative 15 centimeters from 4 to 1 hours. There is less snow at 1 hour. Okay, I'm looking at the change from 4 hours to 1 hour. I'm looking back in time. And if the snow was accumulating from 1 to 4 hours, that means there's more snow at 4 hours than 1 hour. In turn, there has to be less snow at 1 hour compared to 4 hours. Okay, so there's less, I'm looking from 1 hour to 4 hours. So that direction is important. Okay, let's try one more. This is the most complicated it can be. So here's one more. Same thing, for mathematics-wise, I just want to get the area from x equals 3 to x equals 1. So right away, it says from x equals 3 to x equals 1. Will delta x be positive or negative? Well, I think we know we're going from 3 to 1. That goes to the left, x equals 3 to x equals 1. So what is the change from 3 to 1? It'll be 3 minus 1. Whoops, other way around, sorry. 1 minus 3, and that's going to be negative 2. Delta y will be, again, I compare. Oh, this graph is different. Look at this. This graph is different. F at x, in this case, is negative 4. Okay, f at x is negative 4. So that means, like, here's your x-axis, here's your y-axis, right? It's still snowfall or snow melt. By the way, if the snowfall or melt rate is negative 4, are you getting more snow or less snow? Well, the snowfall rate is negative 4 centimeters per hour. If you have negative 4 centimeters per hour moving to the right in positive time, then of course you're going to have less and less snow every hour. So it's melting. A negative rate in this case indicates that snow is melting. Okay, so I want to go back up here. So the change in x from A to B is negative 2 because we're going from 3 hours to 1 hour. And then we always measure delta y, and my arrow's wrong here. My arrow, I always start from y equals 0, the x-axis. That's always my starting spot, and then I go to where the function is. The function is f at x, or y equals negative 4. So what is that distance with direction? Well, it's 4 units, but it's in the negative direction. We always start at 0, okay? Y equals 0, the x-axis. So our delta y is negative 4. So if we look at this, then that's negative 4. So delta x and delta y are negative. So right here, I'm going from 3 to 1. Delta x is then automatically negative 2. Delta y is negative 4. Okay, so delta y, delta x equals negative 2 times by, negative 4 times by negative 2, which is positive 8. Okay, again, just use your signs there. So again, let's go through this for a real-life context. We know our units are centimeters. So now I'm looking back in time from 3 hours to 1 hour, and the snow was melting. The snow was melting. So how did the snow depth change from 1 to 3 hours? Well, it would have to get less and less, so it was negative because it was melting. So if I look backwards in time from 3 hours to 1 hour, was there more snow at 1 compared to 3 or less? Well, obviously there was more. So it follows then that if I look back in time and snow was melting, there's more snow. Okay, so this worked out to be positive 8. Means the depth of snow changed by 8 centimeters from 3 hours to 1 hour. Okay, folks, from the depth of snow changed by 8 centimeters from 3 hours to 1 hour. So that gives you just a bit of an introduction to this stuff. Go ahead and watch this again if you need to, but we will. You'll have some more work to do on this shortly.